I've been doing a lot of work. My lab is working with neural networks. I'm a fan of neural networks in a lot of ways. I do disagree about how people are testing some of these neural networks and the claims that they're making about these neural networks at the moment. And I was just struck by there was almost no reference to psychology. That's where the mind comes in. It's like, how can one make a claim that this is the best model of human vision and ignore 100 years of research in human vision carried out by psychologists? Psychology just gets no respect. I mean, we need more, people need to pay attention because psychology has the beautiful data and relevant data for so many things.
This is Psychology Inspired. Just kidding. This is Brand Inspired. I'm Paul. But this is a Psychology Inspired episode because my guest today is Jeffrey Bowers, a psychologist and professor at the University of Bristol. As you know, many of my previous guests are in the business of comparing brain activity to the activity of units in artificial neural network models, when humans or animals and the models are performing the same tasks. And a big story that has emerged over the past decade or so is that there's a remarkable similarity between the activities and representations in brains and in models. This was originally found in object categorization tasks, where the goal is to name the object shown in a given image, where researchers have compared the activity in the models that are good at doing object categorization to the activity in the parts of our brains good at doing object categorization. It's been found in various other tasks using various other models and analyses, many of which we've discussed on previous episodes. And more recently, a similar story has emerged regarding a similarity between language-related activity in our brains and the activity in large language models. Namely, the ability of our brains to predict an upcoming word can be correlated with the model's ability to predict an upcoming word. So a common claim is that these deep learning type models are the best models of how our brains and cognition works. However, this is where Jeff Bowers comes in and raises the psychology flag, so to speak. His message is that these predictive approaches to comparing artificial and biological cognition aren't enough, and that approach can mask important differences between artificial and biological networks. And what we need to do instead is start performing more hypothesis-driven tests, like those performed in psychology, for example, to ask whether the models are indeed solving tasks like our brains and minds do. So Jeff and his group, among others, have been doing just that and are discovering differences in models and minds that may be important if we want to use models to understand minds. So we discuss some of his work and thoughts in this regard, and a lot more, of course. Show notes for this episode are at braininspired.co/podcast/165. On the website, braininspired.co, you can also learn how to get more Brain Inspired stuff by supporting it on Patreon, or you can sign up to get a short video series that I made about some of the open questions and challenges in understanding our brains, our minds, and artificial intelligence. All right, thank you for being here, and thank you for your support. Here's Jeff. Why do you hate brains and artificial neural networks so much?
Yeah, a lot of people think that about me, and it's really not true. I've been doing a lot of work. My lab is working with neural networks. I'm a fan of neural networks in a lot of ways. I do disagree about how people are testing some of these neural networks and the claims that they're making about these neural networks at the moment. So it's, and I do think, ultimately, I think, what I would like to do is improve neural networks to make them better models of the visual system. I've focused quite a lot on vision, but I'm also interested in other domains, language, and so forth. So, yeah, the goal isn't to somehow reject them. The goal is to improve them. The goal is to have a better assessment of how similar they are to the human visual system or the other memory systems or language systems, because you really can't improve a system until you have a better understanding of how good the correspondence is. So I would also say is, I do think, these kind of, in the case of vision, these so-called image computable models, these models that actually take photographic images and classify them accurately in impressive ways. And it is certainly, no doubt, an amazing engineering feat. So there's no question about the engineering feat about this. But I also think they're not the only game in town. They're not the only way to gain insights. And so I'm a fan of deep neural networks as a promising approach. I think it needs to be approached differently, but I'm certainly in my own research using them. But I also think models in psychology, maybe models in neuroscience that are not image computable, but they may nevertheless be insightful about how the brain works. And in the end of the day, a model really, I think, is designed to increase our understanding of the human brain. And that's the ultimate criteria you need to judge a model by.
Well, you just mentioned the human brain, and I want to come back to that. But when did you get interested in helping improve these models? Was it, with the advent of, AlexNet or something, 2012? Because I know you have a kind of a long history of arguing for symbolic cognition over parallel distributed processing, and then just to bring it back to the human mind or the human brain. Then I thought your interest was more in the human mind than the human brain.
Yeah, well, good. I mean, they're obviously, I think the brain, when it works, it produces mind. But you're right, in the sense that I think, so way back in the, I got my PhD way back in like late or early 1990s, not that long after the PDP stuff was going on. I found it very exciting about that. And it's true, I was quite interested, and I continue to be interested in, at the time I was kind of somewhat critical of, or at least the big debate back then was distributed versus localist coding in psychology. And I was kind of at least open to the idea that localist coding, so-called grandmother cells, might be a useful way to think about how knowledge is coded in the brain, or at least not rule it out. So way back when I was interested in that debate. And then, I guess, for a while, I continue to be interested in it all along. But with the, AlexNet and all this excitement, I think what really it generated my interest of late, or by late, last, 7-8 years now, is all these strong claims being made about how these are the best models of human vision, or fundamentally improving our insights into how the visual system works or the brain works. And I was just struck by there was almost no reference to psychology. That's where the mind comes in. It's like, how can one make a claim that this is the best model of human vision and ignore 100 years of research in human vision carried out by psychologists? And it just hit me as, you go to the reference section of some of these papers, and there's virtually no, or very few, if any, articles published from a psychology journal. And so, I think that's been a theme of my thinking, because I've dabbled in various different areas. And I think one thing I've always tried to emphasize, argue in different contexts, that psychology has a lot to say. So I think sometimes people, jump on neuroscience or artificial intelligence, and they ignore psychology. And I'm fundamentally a psychologist, and when I see these claims being made with not enough reference to psychology, that just kind of irks me a bit, I suppose. So that got my attention, and so that got me back and get it. Like you said, I was way back in the 90s interested in some of these questions, and I kind of got invested in, researching, things got updated. There's lots to learn. And I was just, in a way, struck. And an interesting feature about how things have changed, I think, is back in the 90s or in the late 80s with the PDP, McClellan and Rumelhart and Hinton back then, they were using neural networks, and they were really much more informed, I think, by psychology. So they really
They were a lot of them were psychologists.
A lot of them were psychologists, and so they really focused on trying to account for psychological phenomenon. And then, was it 2012 is it AlexNet or something about that time. And subsequently after that, a lot of excitement. But that crowd, first, the actual remarkable engineering successes was computer science. And then people who got more interested, kind of starting to, again, relate this to the brain and mind, more the brain, because they more focused on trying to predict neural activations in the brain. And so again, there are claims again about links between humans again, but there was less contributions from psychology. And I think that was the big empty space that I decided to walk into.
That's often pointed to by, modern people who use, let's say, convolutional neural networks, people like Jim DiCarlo, Dan Yeomans, and that ilk, is that these models, which were not built to, which were engineering feats and were not built to model specifically the visual system, even though convolutional neural networks were born out of the Fukushima neocognitron and what we knew about those sorts of the way that the human visual system is supposedly set up. But the astounding thing was that, lo and behold, when you actually do compare these models to brains, it does predict through linear regression, predict neural activity. And, even more recent, if we're sticking to vision, more recent work, even you can find a cell and figure out what image, however bastardly, non-ecologically valid that image is, what image will drive that unit the most, right, in a living brain. And so that is sort of the astounding thing, right, is that these quote unquote best models of vision, and you can riff on this if you'd like, best models of our human vision were not born out of neuroscience or psychology, but were born out of engineering would be the claim.
Right. Well, that's the claim, I suppose.
That's the claim.
Yeah, that's the claim. One of the findings, I think the main kind of finding that is used as empirical evidence that these models are like the human brain is their ability to predict brain activations. And it looks impressive at first, but there's a base, what we know of, basic fact about statistics is that, a correlation is not causal. And you can have confounds that can predict quite well. So you can predict off things that have no mechanistic similarity. Just the mere fact that something is predicting something else is, I suppose it's a necessary, but certainly not sufficient condition to conclude that there's a similarity there. And what you normally do when you're concerned that confounds might be driving a prediction is you run an experiment. You kind of vary independent variables, trying to rule out certain possible bases of the prediction, and say, okay, if I vary something, how does that impact in the prediction? And and psychology is full of the basic experimental method where you manipulate things, you understand something about how something works by running an experiment. And those, to me, are the kinds of findings that would be much more, they're more theoretically informative. You learn something if you if you manipulate something and you find what affects something and what doesn't, that gives you some conceptual insight of what's driving, how is the system operating. So I just think good predictions by themselves are not secure in knowing how similar the system is, and it could just simply be a confound. In fact, prima facie, that just seems like very likely, it is a confound in the sense that what we know is, I know you're familiar with brain score, and they've ranked hundreds of models on trying to get the highest brain score. But if you look at the models in the top of the leaderboard, it doesn't matter, look at any of these models, but even at the models at the top of the leaderboard, they classify objects in the most fundamentally different way than humans could be, which is they rely on texture, and they largely ignore shape. So there's just immediately a bit of a paradox there. It's like, how can you have a model doing good predictions about human object recognition and miss the step number one. I mean, I just don't think you could have a more basic criterion of developing a good theory of human vision, at least at object recognition, is that your theory should be caring about shape and shape representations. I mean, there's a lot more to say about what kind of shape representations you want, but let's just start with step number one. It should encode shape. Now, the fact that a model that doesn't rely on shape gets a high brain score should raise serious alarm bells. And there is a straightforward way that could happen, which is there could be a confound that's driving the good prediction. So, for instance, the shape of an object will correlate with its texture. I mean, so airplanes have a certain shape and they'll have a certain kind of texture, and cats will have a certain shape and a certain kind of texture. Now, you can predict potentially a shape representation in a human brain on the basis of a texture representation in a model. And so you could make a good prediction, but it's due to a confound. And then, in fact, people like Robert Garros did this lovely experiment. They ran a controlled experiment. They ran these studies where they said, well, let's run an experiment. Let's attach the texture of an elephant on the shape of a cat and see how the model classifies that object. Because the higher the brain score you get, you'd never know the answer. Is it texture or shape? Well, you couldn't know. You'll never know. You could get 100% prediction and you wouldn't know on what basis is the good prediction being made. The way you find out is the way people have always done experiments. You manipulate something. And so Robert Garros and colleagues did that experiment, and they found, lo and behold, these models recognize things based on their texture. So, it just seems like, well, hold on, there's something seriously problematic with brain score as a measure when you get a high score and you've failed on such a basic criterion. Now, I know it's interesting. I still don't think it's, we can talk more about this, but I don't think it addresses the problem deeply. But nevertheless, it's interesting that there are these new models, some transformer model with, 20 billion parameters trained on, how many, 30 billion images or something like this.
Yeah.
And that model does start to pick up on shape rather than texture. So people point that out. Oh, scale is all you need. I mean, more training, and then in fact the model picks up on shape. And I guess I have two responses to that is, it still doesn't point. It's still the case that the models on brain score, the top scoring models on brain score, recognize things based on texture. So that raises question on the predictivity measure by itself. I mean, and but then and then when people find that, I can get a model to recognize a cat that has the skin of an elephant as a cat, like a human does, that's great. But that's still a pretty low bar in terms of our understanding of how human vision and shape representation. We know a lot from psychology, from lots of research over time, about the nature of the shape representations that are employed by humans when they recognize objects. And so that's fine. It's great that you're recognizing based more on shape and not based on texture. But to claim that then a model of human shape representation is a big jump. You've now passed step one. But there's lots there's lots of stuff we could do if you paid attention to the psychological research. But that gets me back to my, the thing as a psychologist, I'm really trying to, get people to pay more attention to psychology. And there's a lot of interesting research out there. And I think people would find out that these models are failing and are more dissimilar than they think. But the great thing is, once you find a failure, I mean, the Garros is a lovely example. As soon as you ran an experiment, you found that there is a failure, that is, it's relying on texture, not shape. It immediately generates a hypothesis of the kinds of things you need to do. At least now okay, our model has a particular type of problem. It has a problem that it's not working on shape. And then people like Garros, their first intuition was to train the model differently with the kind of data sets in which shape was more diagnostic than texture. That was their, so they didn't change the model, they changed the training space, which is fine. I mean, the particular training they did was not particularly psychologically plausible. What they did is they said, okay, let's take the shape of a cat and attach the texture of an elephant to the, there's 100 different kinds of textures. And each time, so now that, the shape and not the texture is diagnostic. So that's obviously not human-like, but other people have done more realistic training environments and found that, okay, you can start getting but you can start getting in the direction of getting a shape bias with better training. That maybe different architectures will do a better job as well. But the thing is, when you ran an experiment, you knew what to try to fix. But if you just did brain score and you got, I got a brain score of 0.5, and then the next model gets a model of 0.56. I mean, what have you learned? I mean, what do you know? Have you learned, that means it has more of a shape bias? No, you don't know that. You have no idea what the increased predictivity advantage is due to. So anyway, that's what's good about it. I mean, an experiment not only starts removing confounds, which is important, but it also gives you a conceptual understanding of what the nature of the failure might be, or the nature, hopefully, of the success sometimes. I mean, it gives you a better understanding. And that, that's just like, running experiments. Why, it's fine to run, big regressions on big data, just observational data sets, but it's better to run an experiment if you can. And this is a domain where you can run experiments. So why not?
As you're talking about the shape versus texture, it made me wonder, and you would know this better than I, sorry, this is an aside, but are there disorders of human cognition where that is reversed and you could find maybe a model for some disorder in these great vision models?
Yeah. I mean, there's certainly various forms of agnosias. And so you definitely can have, I mean, normally I think of agnosias as disorders of shape perception. There's various different ways in which shape perception breaks down. Offhand, and I used to know this literature, but I haven't followed it in a while. I don't remember people, a form of agnosia which people make judgments based on texture. It's certainly the case that people, if you have prosopagnosia, you might be recognizing things on local features, which actually is a little bit like a neural network might do sometimes as well. And so you might recognize somebody because they have a big nose or, some particularly distinctive feature. So, and you're not recognizing faces in the normal way. But whether it's texture or some local feature, but it's possible, but it just hits me as an odd.
Yeah,
it's like maybe, okay, you train a model to classify objects accurately and you get a good theory of disordered human vision, maybe, but you'd have to then run experiments to test your theory. Okay, it's just really like a form of, there's going to be a vast, large, interesting neuropsychological literature that would probably then something that you should run experiments to determine whether that's true or not.
So running experiments, a current controversy maybe, or a current criticism of the way that, for example, neuroscience has been done the past 50, 100 years is that the experiments are too controlled, and that the animals and humans that we're experimenting with, that because they're not ecologically valid situations, that we're going to get results that are tailored to the experiment or the experimenter and not how it's actually working in the brain and or mind. And in these like really highly controlled, low number of stimuli kind of experiments, that's kind of, what you could be getting. But then these giant data sets that the deep neural networks are trained on should, in theory, dissolve that they're not ecologically valid. And actually, I'm going to ask you about what vision is for in a second, because object recognition and categorization, is that what vision is for? But inherently, these models that are trained on so many different types of images and categories, you would think in principle would, if they are constrained like human vision is constrained, would have a shape over texture kind of bias in that one example. I mean, there's lots more examples that you list in your recent paper as well.
Mm-hmm. So is the question, should, I agree that there are, there's no doubt dangers on both sides. I mean, you could run experiments with, artificial stimuli that, you're missing the big picture, I suppose. But, so many of these studies, what is like a line drawing of an object? I mean, what's so striking is we can recognize an object by its line drawing. In fact, there's a kind of I can't remember the name of but a study done in the 50s, I think it was. I can't remember the author offhand. But he did this bizarre developmental study. Well, not bizarre, but kind of, I think it might be ethically questionable today. But so he raised his child with kind of ensuring that he never saw a line drawing. So until 2 or 3 years old, they did their best not to let the child see a line drawing. And then eventually, so they had to, I suppose, turn off the TV when cartoons were on or whatnot. But eventually, it became too difficult to continue this thing. So, but the child was old enough, I don't know, 3 or something like that, or 2 or something like this. So the big moment happened is, okay, take a look at this and tell me what you see. And they showed line drawings, and it was trivial. I mean, it wasn't even there was no, you certainly don't have to train a child to see line drawing. So there's an artifact. It's artificial in some sense. I mean, until cavemen drew on walls, there weren't line drawings, but it was, that's an artificial stimulus, but I think it's very informative about how human vision works. I mean, illusions are such striking things to me. I mean, I just seems like, they're artificial. I mean, sometimes, there are real illusions that occur in the world and in natural context, but it just seems odd to me to think that those aren't important constraints on how the human visual system operates. And to call them artificial would be, well, that's, we kind of, that's what, an experiment is. You kind of find particular circumstances and it works, when something happens, and that just seems important to me. I mean, but the thing is, in deep neural networks, and this is sort of what I'm doing with, I have a team of people. So in fact, the people on my team are doing all the research, all the modeling. I can't model myself. So they're doing all the actual hard work. And the point is you can run experiments on deep neural networks. So that's what you should do. That's sort of the main, one of the main messages. Another message is, there are other approaches to modeling as well that we should dismiss out of hand. But what I'm doing in our lab is running experiments on deep neural networks. So there's no reason why, if you're absolutely committed to having an image computable model, and I think this commitment is, it's a nice thing to have an image computable model, but I just don't think that's the entry point to doing good research, but anyways, all right, say you want to work with image computable models and you want to ignore any model that's not, okay, that's, you're free to do that. But what you really shouldn't do is not run experiments with your model. You should run experiments and find out whether these, artificial stimuli are producing results that resemble human results. And if they don't, you might have, I'm sure there are some phenomena that are potentially not interesting. It's not that you have to count, I think some phenomena are no doubt more interesting than others, but, but recognizing things based on shape is not one of the things you can ignore safely.
One of my favorite examples that you give in fooling artificial networks or showing that they don't categorize the way that humans do is the single pixel example.
Yeah. Uh-huh.
Can you just describe that, and then we'll come back to, and then I'll have some follow-up questions.
Sure. Yeah, so this is a experiment run by Gaurav Malhotra, where what we did is just added a confound in a stimulus set. So we use this very simple data set called CFAR10, which is just 10 categories, each with think 60,000 images. So it's compared to what's normally used, ImageNet, much smaller, easier model data set to work with. And we simply added a pixel, we had different conditions, but one of our conditions was a single pixel where you'd say, okay, every time you see a plane, put a pixel of a certain hue in this location or in this, at least this small region of space. And every time you saw a horse, you put it over here. And every time you see a bus, you put a certain pixel over there. So now there's two kind of diagnostic cues for the classification that a model in principle could pick up on. They could pick up on the overall, shape or texture. In fact,
texture. Yeah.
Probably overall texture, really. But anyways, something that you think, the whole image itself is used. Or alternatively, you could do it, sometimes called a shortcut. You could just exploit this single diagnostic pixel. And that's what the model does. The model will decide, it's a lot easier because the model does, the model just wants to classify it. There's no reason it should do it like a human. And so when given those data sets with this kind of confound that we just artificially inserted, the model chooses that shortcut. And so what happens is that if you then at test give a picture of a plane, but put the pixel where a bird was, the model will, from a human person, it looks exactly like, I can't remember what I said, a plane.
Horse.
Whatever it was. But the model will jump in and say, it'll say, I think that's a bird, because it's just, all it knows is the pixel. It doesn't learn it. It's just focused on the pixel. So, because
the pixel in that case is the most predictive thing of that category.
Yeah, it's the most predictive, or at least it's the easiest thing to pick up. They're both, in principle, the human could, pick up on either, and if they're, it could get essentially and see both are, at some level equally predictive, but the prediction at the level of the image is a more complicated, challenging set of invariances that it has to pick up on. It just picks up on the simpler feature that it can pick up on. Whereas a human being doesn't even notice there's a pixel there.
Right.
So, and data sets are just full of confounds. And sometimes, it's nice in our experiment, we know what the confound is because we inserted it. But in naturalistic data sets, God knows how many confounds there are. And, some of them you won't see, but, some of them are things like what texture is correlated with shape. That will certainly be one. And that's no doubt, I think, why models, to our surprise, I don't think the expectation was prior to Garros that the model, was relying on texture, not shape. But it turns out it did, because that's just an easier feature to pick up on.
In something like cancer diagnosis, right, where a deep learning network is being used as a tool to look for anomalies or some, detect pixels, that's like little clusters of pixels, right? That might not be detectable by the human eye. In that regard, you would want a superhuman, for lack of a better term, a machine that can attend to all pixels equally well and doesn't run out of energy and can make decisions based on taking in entire images and statistically go over all the pixels and see if there is any anomaly. On the other hand, that's not how humans work, even though we can get pretty good at that kind of stuff. And then there's the question of whether we want these things to work like humans or to work differently than humans or better than or just differently, or whether it even matters. Why would it matter for one of these networks to function the way that a human mind or brain does?
Yeah, if you're an engineer, it does. My critique doesn't apply. I do think if you take the example of these models that are trying to detect cancer and things or make diagnoses, it turns out that these models often pick up on confounds that you don't want them to pick up on, because it turned out that there's just is a particular logo on the hospital, corner, or there might be, if people are lying down versus standing up, there might be some weird kind of configuration that you weren't aware of, but actually the model picks up on that. So confounds are a problem in that pure engineering context as well. But if you put away, if you put aside the fact that, if the confound is going to allow you to, on a test set, diagnose correctly. You don't actually care in a way. I mean, if it's picking up cancer cells or some extra correlated thing that's associated with cancer cells, and you thought it's picking up cancer. In fact, it's picking up, a byproduct of cancer. Who cares? As long as you're correctly identifying some X-ray that's needs to be picked up. And then it's fine. I mean, I don't, models can outperform players in chess and Go, and and that's, I have nothing but kudos to any engineer that built this stuff. Fantastic. I mean, it's impressive, and who would have thought?
But also from an engineering perspective, there are people who are interested in building, generally intelligent agents, right? Someone who could detect cancer perfectly, paint your house perfectly. I don't know, tell you what cartoon you should watch next perfectly, whatever that means.
Yeah.
And which is a different task than understanding the brain and mind. And I understand that you are more interested in understanding the brain and mind than, building these sort of I know that you are interested in generally intelligent agents, but I mean, how much of the mind and brain do we need to emulate if we want to build generally intelligent agents? And if you know what a generally intelligent agent is, you should let me know.
Yeah. Well, I mean, I think, one of the messages that we're doing in our research is that there's often, multiple ways to get an outcome. There's shortcuts. So, you can classify images based in ways that, you didn't think, wasn't the way you imagined. There's probably multiple ways to achieve some goal. And, if you can get a car that can drive you home safely at night based on training it on trillions of miles of simulated driving and things like that, I'd be happy to have if once it works, I'm all for it. But the idea that that's how a human learned to drive would be, absurd, because it's been trained on a trillion miles of data. But if you could train a model on all relevant human skills, and you just have a whole collection of, you train it with an exorbitant amount of data in the driving context, and an exorbitant amount of training in language context, and an exorbitant amount of training on image data sets, and and motor, motor robots that are somehow eventually trained in ways, you can capture all the forms of intelligence that would be useful for us. If then I'm all for it. It's just, but like you say, I'm a psychologist, so to me, the question is, to what extent is success on these tasks a demonstration that it works like the brain? But yeah, I don't have any magic definition of what general artificial intelligence would be, but I guess a model that just was very useful in helping us in our daily life and doing all the things we want to do. I suppose that would be, a practical way, but don't confuse that, or just at least certainly don't assume that that's a human-based solution.
But you think it's worth continuing with I'm just going to put everything under the deep learning umbrella, and then to understand our brains and minds better, and if that's correct, what is the solution? The term inductive biases is thrown around a lot. We need to put more, constrain these systems in a way that we're constrained more, that we have to move about the world. But, are we gonna have to essentially emulate all things that humans and animals do to build and test these systems correctly? Or since there are multiple ways to skin a cat, are we going to find 14 different unique solutions until, once you're satisfied, to eventually satisfy you, rather?
So you're asking me now back to emulate the brain as opposed to just solve an engineering
Not
task.
just yes. I mean, whether, yeah, I mean, how much are we going to have to emulate the brain to understand the brain and mind?
It's a good question. I'm skeptical that we're going to be able to, use I mean, the one approach that people are adopting is the scale. Scale is all you need. More training.
Yep.
Basically use the architectures. Okay, maybe go from convolutional models to transformers, but somewhere we got something as architecturally we're kind of close, but the training environment or the objective function or some extra, and that may be, and proof is in the pudding. Run experiments and find out how far you get. But there are just such striking differences between what these models look like and what brains look like, and the assumption that all these models have units that are effectively all the same as each other than the connection weights they have to other units. So, we're and they're not spiking. So we have if you look at a brain, there's hundreds of different types of neurons that have incredibly different, diverse morphology, and they vary in ways that would, potentially be important computationally. They have different, time constants as how long they integrate information. They conduct information at different speeds, and they have spikes in which the timing of spikes is really quite essential into whether information is communicated. And, there's endless other kind of differences. And sort of the assumption is that we can ignore all that. We can kind of assume they'll be functionally equivalent if we just train a model in which the only adaptive area of change is the synapse between units, in which everything works in fixed time steps and there is no other form of variation. Now that may be true, but it would be, if you want a model of the biology of, maybe as a psychologist, I tend to imagine that these forms of variation matter, and they may give you some capacities that you wouldn't otherwise have, or even if they don't give you additional capacities, they make you manifest your capacities in a certain way that are interesting from a psychological point of view. So just to ignore all of that is a big gamble, and again, test your model to see if it works. But I wouldn't be surprised if you're missing something important by ignoring all these forms of variation. And I guess the assumption is people often talk about, when we train a model endlessly, with more and more, we're going to eventually get there. It's like as if the learning of the model, some combination, some of the learning is sort of like the in-life learning, the learning that happens in a lifetime, and a lot of this other training is sort of emulating the evolution in the first place. Somehow you just can get everything. So I don't know which part of my outcome was a product of what we'd call evolution and what we call learning, but at the end of the day, the answer I obtain is a lot like the brain. But the thing is, evolution's not constrained by changing just the weights between neurons. Evolution produces whole varieties of, again, a wide range of morphological forms of neurons, all of which, may change. The architectures change, the properties of the neurons change, and all of that is outside the scope of these models that just change their weights. So whether you're in the possible space of a solution that's going to be a biologically, interesting, a close correspondence to humans, is a big. It's certainly a failure at the single cell, at the neuroscience level, at trying to understand. If you say why do we have this morphological diversity of neurons? Well, you're not going to get an answer from a model that has every neuron the same. Whether you'll have a psychologically equivalent model that, okay, we could just ignore those forms of variance and we'll get a functionally equivalent thing. Okay, well that's in the realm of possibility, but it's not I don't think we should take it as a safe bet, but one way you're never going to find out is doing more brain score. You're going to have to run experiments to see whether these models function in the way that a human visual system functions or a language system functions. But it just seems to me a very unsafe premise to assume that just changing weights, that the only relevant form of learning and computation in the brain is in synaptic changes, and ignoring other forms of variation in the brain. Anyway, I'm just repeating myself. It seems unsafe.
Yeah. Yeah. So in some sense, okay, so I'm sure you're aware of the idea of multiple realizability, and people like Eve Marder's work who show that given like the same set of a small number of neurons, you can still, there are lots of different ways that you can come up with a behaviorally relevant behavior outcome to produce the behaviorally relevant outcome. I'm repeating myself now. And in some sense, though, like, so then you have this like problem space in Eve Marder's work. It's like the stomatogastric ganglion, right? So the problem space is how to digest food and stuff and contract the muscles in a certain way. And that constrains, in some sense, constrains the possible solutions, although there are lots of different solutions to do that. And so one of the, again, I'm at a loss maybe to ask you a question about this, or maybe just ask you to comment on it. One of the impressive things maybe about neural network models is that even though they are so divergent from our biologically realistic, because they're biological brains, that maybe if the problem space is the same kind of problem space, they'll converge on a solution within the space of possible solutions that are still valid, right? But then that goes back to the question of like, well, are we just giving them the wrong training data, or are we asking them to solve the wrong problems? So this is where I was going to ask you what our vision is for. Is our vision for object detection?
Yeah. Well, almost certainly that's not the, I mean, we can classify objects and we can label objects, but, our visual system obviously evolved from, vision's been around a long time. I don't know how far back vision goes, and evolution's kind of descent with modification. So we've adapted our visual system is based on much more it's species long gone, and I don't think they were labeling the images in their world. So the visual system is no doubt, and so our evolutionarily in time scale, it wasn't all about that, and then in our own lives, it's not all about that. I mean, obviously we manipulate objects, we walk around the world. One of the ways that people talk about things is that, what we're doing is trying to infer a distal representation of the world. So we have this 2D image projected on our retina, and we're trying to infer a three-dimensional representation of the world. And it's an ill-posed problem. I mean, we have, going from 2D to 3D means that, in principle, there's they're infinite in principle, different worlds out there that can project the same 2D image on our eyes. We need to kind of have some assumptions about the likely causes of this image on our retina. And that's where these kind of various priors come in. But the argument is, we're trying to build a 3D representation, because a distal representation of that world. Because once you have a distal representation, ideally you can do lots of things with that. You can reason about the objects. You can grab them from different points, different perspectives. You can do lots of things. Whereas, models, more and more people are developing self-supervised models, and so not all the models are only classifying images now, but most, the models in BrainScore, for the most part, they don't compose a three-dimensional representation at all. They're taking a 2D surface representation of texture and labeling it. There's no attempt to infer the distal representations of the objects in the world from those images. It's just a 2D mapping onto a label, and that's clearly not what our visual system is doing. Again, what do you make of that fact that you get a high brain score in a model that's not composing 3D representations? It's not organizing the scene by Gestalt principles or performing constancies, or all these features that we know about human vision are just not part of the task of, or they're certainly not they're not necessary for a model that's trained in a supervised way to classify 2D representations in a labeling task. And the hope, and I think it's definitely worth pursuing, is that if you get much more sophisticated training, a much more realistic, a more realistic data set to train, and you're not classifying static images, but you're predicting images, and you're developing an embodied representation in the world, and you're kind of developing a robot that's kind of learning and grabbing things. Almost certainly, I don't doubt that some of the things that we see in human visual properties are going to manifest themselves in a much, once you have a much more realistic training and a better objective function. I wouldn't be surprised at all if more and more of these properties of human vision start manifesting themselves in a deep neural network. But I also wouldn't be surprised if some things are just outside the scope of current models. They're just not going to ever find themselves in the human space because they're just working with neural networks that, for one thing, don't spike. They don't have morphological diversity in their units. And they're not the product. They didn't start from the evolutionary starting point that human visual system worked from, which at times had very different functions in the first place. I mean, there's lots of things that, our bodies, you never would have ended. If you started from scratch and you tried to evolve something, you probably wouldn't come up with the solution that humans have done. But the reason humans ended up with a solution that was sort of adaptive, having a weird evolutionary history. And you started, once you get to this place, the best solution's here, but you never would have started there. And I don't expect, even like the silly thing that our photoreceptors are in the back of our retina, right? So it's like we have all this light that's, it's going through 3 layers or more of other neurons in the retina, and we have a big blind spot because the ganglion cells are leaving from a part of there, and you have veins blocking the light, and all these different things. I mean, if an engineer wouldn't decide on adaptive grounds for that. I mean, it turns out that there's lots of other constraints that you have. So
humans have it hard. Animals and humans have it hard.
Yeah. I'm not sure. I think the octopus. There's some weird animal that doesn't have them. The photoreceptors are at the front of the retina. So there's like one. I think it might be an octopus. I don't know if octopuses have eyes. Maybe I got really wrong there. But there's some animal that doesn't do it. But I think for some reason most animals have the photoreceptors at the back of the retina, which just from a surprise, And then the visual system is confronted with problems that it wouldn't other. And so there are these interesting ways in which we have filling in processes, and there's a whole, there are ideas. People have developed, like people like Stephen Grossberg and others have developed interesting architectures that are trying to rectify the terrible signal that's being projected to the photoreceptors. But that's just sort of like. So there are actually important, cognitive, visual, low-level visual processes that may be only manifest or only required because the nature of the input. But these models, they don't have those problems. In fact, they have just tend to have equal acuity across the entire space, and they don't have any. Yeah. So whether if you train the model more and more stuff, but you didn't work on getting a more realistic retina, you may end up again with a very, missing important parts of filling in phenomenon and, things that, might not, it's not even a problem to solve.
Well, maybe octopi can't fill in. That's something to test. Thinking about our evolutionary needs and projection, I mean, do you think that homeostatic needs and life processes, a sense of autonomy, and the fact that our bodies regenerate and have to maintain itself? I mean, how important do you think that is to our "quote unquote" higher cognition?
Ooh, that's a good question. Yeah, I mean, I think I may not be answering your question, but things like, I sort of get the sense, embodied cognition, I think, is,
Sure, but that's just a robot. Where a robot doesn't have to be autonomous. We can just give it a battery. It doesn't have to maintain itself. For instance.
Yeah. Well. Yeah. I'm not 100% sure I know what you mean, but I do think that hey, they'll have achieving homeostasis is certainly to be important for the hypothalamus or the hypothalamus.
Yeah, the lower brain
bits, the lower bits for sure. The higher bits, I expect so too. I expect everything is going to be at some level constraining. Whether that's the place to constrain theories of human vision. That may not be the place to start. I mean, I think, but.
Do you think that we, let's say just humans, right, are implementing algorithms, straight up algorithms and objective functions, or is it messier than that? Or, is that just like an algorithmic solution to something, a necessary means to attain that thing, whatever the algorithm that's needed at the time? Or do you think that we have just by hook or by crook come to develop a bag of tricks, I think someone like Gary Marcus might say, to serve as objective functions and algorithms?
Yeah, but everything, I mean, the neural network is, so by algorithm, do you mean like symbolic, some kind of list kind of like?
No, just a set of concrete predefined steps to determine a solution to a problem.
Mm-hmm. Well, I think the brain clearly can do that. I do, I do think the brain does have a bag of tricks. So I think there are, lots of hacky solutions and satisficing in many different ways. So I don't doubt that at all. But we can have an algorithm for addition and multiplication, and so we can kind of very strategically. I mean, I might relate to system 1, system 2, Kahneman kind of thing. So we certainly can implement kind of rational.
What portion do you think?
Yeah, I don't know.
Of our cognition.
I mean, I do think we need some. One of the things that certain types of models of vision or language have are, these compositional representations where you have a kind of explicit encoding of relations and elements that can bind in various ways to these things. And that, again, it's Gary Marcus or people like, Jay Fodor and vision, people like John Hummel and Biederman with the Geon theory, with structural description theories, where you have an explicit coding of parts and the relationships between parts. I do think that's very likely an important component of human vision. I mean, I do think that coding relate. So one of the things I was mentioning before, that it's not enough in the theory of vision just to say, I recognize this thing that has a shape of a cat and the texture of an elephant. Oh, that must be a cat. So that's good because humans do the same thing. But there's a lot more about shape representation. So one thing about shape representations is that we recognize objects based on their parts and the relationships between the parts. And we have an explicit representation. At least that's what we'd argue in some of our research, and other people long before would say. And I think that might be really hard for a lot of these models. I mean, even people like, some people like Biederman and John Hummel developed, or it was Hummel and Biederman in 1992, had this great psych review paper where they kind of implemented the Geon theory of object recognition into a neural network, 30 years ago now, more than 30 years ago. And it has a mechanism by which you do dynamic binding of relations and explicit representations of relations and explicit representations of parts, and associate these things. But even recently, people none other than Jeff Hinton are developing things like capsule networks and this kind of he has this thing called GLOM. It's, I think, a conceptual idea, but he's trying to understand the hierarchical relationships between parts and explicit representations. So, and these are not image computable models. I mean, so he's developing these non-image computable models that, would do terribly on brain score. I presume we get a score of 0 probably or something. But he's developing these models to say you need to develop models that code for relations, and he doesn't do it in the way that Hummel did. Hummel had like synchrony of activation units, and Hinton has some routing mechanism of which I couldn't tell you much about it really, but it's an attempt to develop coding of explicit forms of relations and part relationships between these things, and they in both cases sacrifice at the moment image computability. Ultimately, you're going to need ultimately the human visual system has a retina, and so I agree. Ultimately, you want a model that's image computable, but whether that's the place to start or whether you should kind of work with a quote toy model in order to figure out how can you code for parts relations. And everyone from John Hummel to Jeff Hinton have adopted the approach of playing with toy models to work and try to understand these relations, which eventually you'd try to implement in a full-scale model that's image computable. So I don't know, does that relate to algorithms or not? I mean, I think it relates to the idea of having an explicit encoding of parts and relations and a mechanism by which that's achieved. But it's not like an algorithm of long division.
Yeah. Part of what one of the examples that you were just alluding to, or at least one of them, was, and I don't remember I know you've done work on this also, but basically neural networks will judge if something is same or different based on like some trivial pixel displacement, whereas humans won't be able to tell that difference, but humans will be able to tell if the relations between two, for example, lines are different.
Exactly. That's the kind of research that I'm talking about. So we have this stuff where we kind of, so this is stuff by John Hummel and I think a PhD student of him, Stankovic, back in the 90s, showed that humans are highly sensitive to this kind of the categorical relationships between object parts. In these simple line drawing kind of things, like kind of some people might know this. Tar and Pinker had some kind of simple stimuli, and they kind of slightly based off those things. And so in our research showed that these models, current models, completely blind to these kind of, so they don't care about those things. We even tried to train the model on we'll train it on these relationships, and we left out one relationship, but we trained it on lots of other relationships. Right? So the categorical relationship between parts matters here and here and here and here and here, and then we have a left out one. We say, okay, how and the model ignores it there. So it's just over and over. It's it's not learning the relationship. It's learning some particular local feature, but it's not understanding the concept of a relation that then applies. And that's where people like John Hummel says, well, you're never going to understand these. You need an explicit representation of a relation that can take on any kind of object part, and it's not a conjunction. It's not a single unit or some distributed representation of a circle on top of a square. It's a circle representation, a square representation, a relationship between those two, and that same relation would be involved in representing a cube on top of a cone. I mean, you maintain, and that's kind of the stuff that people like Fodor and Polishin argue for, compositional representations, where the parts, the complex thing is composed of parts, and the parts maintain their identity. You can combine them in new ways, but you don't kind of just forget. You actually have a concept of loves. That John loves Mary, Mary loves John. It's the same love. It's not like these are just different things. Hopefully it's the same thing. Yeah, who knows? Maybe
that could be argued. Yeah,
that's right. Yeah, that's a good example. But anyway, so it's possible some of these massive models will kind of pick up these things in a way that are compositional. But our experience. So I've worked with in our lab. We've used models where we learn what are called disentangled representations. We take these variational autoencoders. You take an image and you reproduce an image as some variant of the input, and you can kind of train in a certain way with certain kind of loss functions that leads the model to learn what are called disentangled representations. So it's kind of this unit in the hidden layer is coding for the exposition of the object in the scene, and this is the Y unit. This is, the level of activation of unit number 3 codes for its shape and so on. So you learn these kind of sort of grandmother-like representations. They're not exactly grandmother cells, but they're kind of interpretable locals. But those models don't support combinatorial generalization. So even once you learn those things, you say, oh, great, now that's the answer. So now I should be able to kind of recognize, I've seen circles on the right-hand side. I've seen, I've seen squares, but I've never seen this on the right-hand side, but I've never seen a blue square on the right-hand side. That combination, having learned those disentangled representations, you still fail when you combine these features in a novel way. So there's I think a challenge about how you solve these kind of combinatorial compositional representations. It's a challenge. And, maybe these models will do it, but maybe you need something, again, qualitatively different than with these models that we're working with at the moment.
Well, I want to ask you about language in a moment because you've done some fun tricks with language as the large language models. But before we leave the vision aspect, taking us back to comparing brains and, two different brains or two different models or a brain versus a model, something that you write about a bunch is representational similarity analysis. And this is a way to basically see the correlation between how a model and its given units are representing pairs of objects, for example, versus how a brain or a different model or something would be. And you don't like representational similarity analysis because you can get a high score saying that the representations are very correlated between, let's say, a brain and a model, and still you have these psychological disparities with the psychological experiments. If I didn't explain that correctly, or if I don't have that correct, you should correct me before I ask you a question here.
No, that's right. That's right.
Okay. Okay. So, and we've talked about those a little bit on the podcast, but we don't need to go into detail on them. Another thing that people are looking at is the sort of low dimensional dynamical structure between artificial networks and brains, especially in like recurrent neural networks, and finding that there's, a similarity between the low dimensional structure on, let's say, like manifolds, and that the trajectory of neural activity through time is similar often between a model performing a task and a monkey's neurons or something performing the same task. I don't know if how much into this kind of work you are, or if you have opinions on it. I was just curious if you did.
Yeah, in terms of the temporal dynamics and showing, I don't know too much about the temporal domain about how, but almost certainly it's going to be another case of it's a kind of correlation. You're taking some kind of representation in the case of some kind of representational geometry in the case of RSA.
Yes. Yeah.
I guess some temporal dynamics in the case of what you're talking about, which I don't know much about, and correlating with each other. But there is an interesting paper that came out. I saw, I can't say too much about it, but it has to do with temporal domains where they show that you can kind of predict, I hope I get this right, but you can predict ups and downs of Bitcoin based on neural activations in a monkey or in a rat, I think it is. So there's some kind of ability to predict well above, and they correct for statistical chance and things based on relating brain activation of a rat and Bitcoin. And one of the and this is I don't understand the details of it, but the reason I'm thinking of it now is that it has to do with time dependency. So it's kind of like you can get these spurious correlations, and it hinges on time dependent things. So if you can it may not apply.
Stochastic things, probably.
Well, it's not. I mean, as long as you have some kind of, the
alpha rhythm or something in there.
There's something. The state you're in now is autocorrelated with what it was before, and you can kind of get these spurious autocorrelations between systems, and it depends on but it relates to the temporal aspect of both Bitcoin moving up and down and neural firing of a rat moving in a maze, and you can just get spurious correlations between these things. I thought, I think, so I don't know, but I just think it's very easy to get correlations that are very misleading. And it hadn't been Bitcoin, but if you'd kind of run something that looked like a model, you might go, oh, look at that correlation. It's just, you only realize it doesn't mean very much when it becomes an absurd correlation that you're measuring. But if it had been, this is my model of something, then it might seem quite impressive. So I don't know. I don't know but I do think that these correlations that are found in RSA, correlations that are found in kind of linear predictivity that you found in brain score, are dangerous because they could be the product of confounds or some other factors as well. There's another thing where just simply the number of independent latent factors, and we can there's some paper that came out just having more sort of orthogonal-like representations in architecture affords better predictivity, independent of whether the representations are aligned. So there might be yet another kind of way in which you can get these correlations that look impressive, but they're not necessarily informative of similar mechanism.
This all reminds me of the dead salmon in an fMRI machine experiment in neuroscience. Where people put a dead salmon in an fMRI machine and recorded a bold signal, which is supposed to suggest that there's brain activity. I think they had the dead salmon performing a task or something. I don't remember the specifics.
I think it was a social psychology mind reading.
Mind reading. Okay. Yeah.
Something like that. Yeah, but I think that's a danger. You get these things, and you can get things that look impressive, but then you can do a kind of a reducta absurdum kind of condition, and you find that actually, the methods we're using doesn't mean it's wrong. It just means it means you need to run an experiment to find out whether this correlation is really producing the similarities that you think that they do.
All right. So we focused on vision so far, and I am aware of our time here, but you've done some fun things with large language models in this same kind of vein. I know you haven't worked with them as much. First of all, I'll ask you the question, and then you can kind of generally tell me, what your thoughts are on large language models in general, and especially, again, as models, the same kind of work that predicts visual model activity and compares it to neural activity. This same kind of linear regression readout has been performed on data sets like fMRI and EEG in terms of predicting an upcoming word, which is how these large language models largely function these days. So maybe what do you think in general of these large language models? And then I want to ask about how they can learn nonsense languages just fine.
Yeah. Okay. Yeah. Well, like everyone else, I'm blown away by ChatGPT. It's like an amazing thing. If you asked me, a year ago, you can have something that actually is so useful and interesting. I would have, so I didn't see it coming. So again, amazing. I know some people are criticizing, and you can find cases where, many cases where it does silly things, but overall it's bloody impressive. So I don't want to suggest it's not impressive, but the next step is it a good model of human language? And so that's a totally different category of fish. And for one thing, it just hits me as implausible in the sense it just seems unlikely that language acquisition is a product of predicting the next word. So the idea that children are
So it's like solely a product of predicting the next word, or the prediction surely has to be a part of it.
Well, I think I would have thought what you're predicting is, you're trying to communicate ideas, and you're hoping using words to achieve an end. You want the cookie, or you want someone to agree with you that that's a doggy or something like this. So you're just going to have reference to the world, and I don't know too much about the syntactic capacities of 1.5-year-olds, 2-year-olds, but I really don't think that the child is, as they're learning language, their primary objective is to predict the next word in a sentence. It hits me as implausible. So in a way, it's sort of another example in my mind. I mean, before we talk about any data, just a striking example of how remarkable similar something can be, because it just generates, flawlessly lovely text, syntactically coherent, now meaningful in terms of useful things.
Yeah.
I don't mean it means
okay. All right. I was gonna.
I don't want to go there, but I would say that I can read this and go, that's a
meaningful to you.
2-1. It's a 2-1 in my essay. A student can get a B. So it's a pretty impressive text that they could write. So, but they can get that from a system that had a completely wrong objective function, or largely. I mean, it's one where you first were predicting the next word, and then you have this weird reinforcement, kind of human in the loop reinforcement component, which is, again, obviously not part of the mechanism by which children learn to kind of generate coherent text. So just as an example of how very different, learning objectives can produce behaviors that are eerily similar to human performance, doesn't mean that they're the same thing. In a way, example I gave, a couple times on Twitter.
I like that.
If you have a model like DALL-E that kind of generates images, you wouldn't say, "Oh my God, that's the best theory of human drawing or painting." I mean, it's an amazing painting. You could sell the painting and win a competition, painting contest, but it's not. It doesn't seem like a plausible account that it's the best theory of human painting. And, you can generate models of coherently meaningful text to a human being anyways, and doesn't mean it did it like in a way like a human did it.
Yeah.
So I think it's a nice example of how different something can be in its objective function and nevertheless emulate behavior in an impressive way. And when it comes to but then you can say, okay, well, that's fine, but Jeff, look at, I can predict brain data, again. So it's a predictivity thing again. But so, there's a paper that came out in PNAS last year, I think, and they were claiming you can account for 100% of explainable variance.
That's shrimp et al., I believe. Yeah.
That's right. That's the paper. And so they have a paper where they're making, it sounds very impressive. Now, the first thing you find out if you go, is that by 100% of the explainable variance isn't that much, because the amount of variance you can predict one brain, a human brain, from another brain is quite small. So, it doesn't account for 100% of variance. It's 100% explainable variance. The explainable variance is very small. So I think 10% or something like that. So, so it predicts 100% of 10%. But then if you look carefully at the paper, you find out that it can predict, in some cases, just as well the brain activations in non-language areas. So it's like, okay, you can predict 100% of 10%, both in language areas and non-language areas. So now I think, what's going on here? And that just, again, highlights, well, maybe these predictions are not reflecting the mechanism similarities that you think. There can be other ways in which you can get similarities that don't reflect mechanistic similarities. It seems to me a problem that non-brain areas are, you can predict those just as well as language areas. I mean, what does that mean? It means that this productivity stuff is not doing what you think it's doing.
Or that language is distributed more highly. And
well, okay, I think, yeah, that may, yeah, I think they have some, they give some explanation about semantics. So yeah, anyway, you could do that, and it's possible, but but all of a sudden the story is not quite so straightforward, and there's some questions that one should raise. Yeah, so there's a bunch of these studies that there's another paper, but even smaller. The amount of variance accounted for is, I don't know, 0.007%. It's significant, but it's so small. It's like, so I don't know. I'm not very persuaded anymore that, I mean, the correlations are much more powerful in the domain of vision, and I'm not very persuaded by them.
Right.
So so that you go to the language domain, they're much much smaller. And I'm not impressed by them either.
Yeah, but it's a different data set, right? Because in vision, a lot of the data sets are from non-human primates where you're recording actual neurons. I'm not trying to argue with you, but I'm just thinking there's probably a lot more variation in the fMRI bold signal and the EEG. Yeah.
Well, it's definitely the case. I mean, because you get much less, what they call a noise ceiling. The amount one human brain can predict another is much lower in language studies than it is in. So so it's not. It's not the fault of the model that the noise ceiling in humans is so low. It's just the data is much more noisy. But that does nevertheless, to some extent, weakens the evidence that one's presenting when one says that I'm accounting for 100% of explainable variance, and then you find out, well, the noise ceiling is awfully low. So that is relevant.
So these large language models can learn English, they can learn Dutch, they can learn French, and I don't know, all the different languages, learn them very well. They can also learn impossible languages, which is what you've taught them to do. You use the term meaning, and then I thought you were going to go toward, I thought you were going to start criticizing, whether these large language models understand the meaning of what they're producing, right? And to me, when I was reading your work on teaching these things nonsense, impossible languages, that speaks against the idea that large language models can understand the meaning of what they're generating. But maybe you can clarify what you guys did, and then I don't know if you have comments on that related to what that means about meaning in large language models.
Yes, this is work with Jeff Mitchell. So so we just trained, so this was a couple years back now. So this is pre-ChatGPT, and these are models that just was purely predicting the next word. There was no other humans in the loop, and so it was generating syntactically coherent sentences. It wasn't generating useful, it would just it would ramble on and talk nonsense. So it didn't mean, the meaning wasn't there because it was just talking rubbish after a while. But
the meaning for us.
Yeah, it was the meaning, even the meaning for us was missing. Although at the sentence level, it might be meaningful to us, but at the paragraph narrative level, it would start rambling off. And that's what the genius of ChatGPT was, I guess, to rein these models in to kind of be more meaningful for us.
Yeah.
But anyways, the models could learn syntactically impressive sentences, and they could do various, subject, verb agreement, a number agreement between various grammatical markers. So so it could do things quite impressively. So in other words, syntactically correct sentences. And the thing that people have been saying recently as well, especially with ChatGPT, is, aha, Chomsky is wrong. I mean, look, we've demonstrated that you can learn syntax, and these models have no universal grammar. They've just been, it's just some generic architecture that's nothing language. It's the same. I mean, in our case, it wasn't nowadays it's transformer, but it's not built. That transformer can be used in visual domains. I mean, you have to modify things, but it's nothing about language. And nevertheless, you can get these syntactically coherent sentences. And so therefore, Chomsky is wrong. But I think that's just a misunderstanding. Like, Chomsky's story was, and I'm no expert on the details of Chomsky for sure, but yeah, Jeff Mitchell might know a lot more than me.
Okay.
But anyways, but the basic idea is that the critical thing about human language is we have an ability to learn a language with relatively little data. A child is learning to generate syntactically competent, grammatically accurate sentences with relatively little input with the claim. That's kind of the poverty of the environment. And so, but that comes at a cost, according to Chomsky. So you can learn quickly, but you have to kind of abide by the rules of universal grammar. So we have inductive biases that allow us to learn certain types of languages, and we can learn them relatively quickly. And so that's so we're constrained in the languages we can learn in a normal way, quickly, in a natural way. But the benefit is we can learn them quickly. Whereas large language models have exactly the opposite properties, which hit me as supporting Chomsky. So these models need lots of data, much more data than a human would require, and but they can learn anything equally well. There are no inductive biases. That's the reason they can learn anything. Is there's nothing constraining them all to learn certain types of things. So the benefit, I suppose, if you want to call it benefit, it can learn anything. The cost is it takes a lot of training. But that hits me as not a falsification of Chomsky. That supports the idea that there's something. It doesn't support Chomsky's particular theory, and Chomsky's theories have changed a lot over time, but it doesn't support any particular theory. But it does seem to me support an idea that there are important, inductive biases that a human being needs in order to learn a language quickly. So that's the main story, I think. And it's, I've heard recently people, again, this is, informal conversations on social networks and Twitter and stuff saying, humans actually do have a massive amount of exposure to language. A child does expose, but I don't think it's appropriate to say, words that they overhear as a child. I mean, if you just passively, the words around you are not contributing very much, I don't think, to language learning. You have to actually, there are studies by, so I think this is right. So I'm saying something that I'm only 90% sure about this. So I think it was Patricia Kuhl did some interesting studies. It may have not been about syntax. It might have been about phonology, but aspects of language where if a child is just kind of watching or passively, being exposed to a foreign language that's on a radio or television, they don't learn.
Right.
So just the passive exposure. So when someone says, "Oh, a child's learning," he's exposed to 50 million words a week or something like that, just because that's how many words are spoken around them, and that's maybe less than in ChatGPT, but nevertheless, it's not crazy. It's like, well, I don't think those are the relevant kinds of exposure. To what extent are children actually engaged in language and parents speaking to the child and that's the more relevant number of episodes, not just a sea of words around them that they might largely be ignoring. I mean, because I do think there is a challenge for these models require a lot of training. Every exposure is part of the learning environment of these models. The child's learning it's not going to be anything remotely as large as what's required to train ChatGPT. So I do think, I think the large language models provide some evidence in support of the general hypothesis that humans have inductive biases to learn certain types of constructions, and they can do it relatively with little data compared to what a model can. I mean, and there's a parallel kind of case that we've studied in vision where we've said it wasn't. I think it was Sami Bengio in his lab a few years, 2019 or something like this, and we've kind of followed up on some of this work subsequently. But they found you can train a model to learn. You take ImageNet and just convert all those million images in ImageNet. So there's like 1,000 categories, each with 1,000 exemplars. And if you just kind of make them all random pixels, like a TV static, so there's just absolute randomness. There's no structure. There's no structure amongst the 1,000 members of category 1. There's similarly no structure of the members of category 2. You can, logically rotate it. So it's just a million random bits that are arbitrarily assigned patterns assigned to 1,000 categories. And you train a model and it can learn it, and it doesn't take that much longer than actual images. I mean, it's sort of like, but that's not like humans. And, in the same way, it doesn't seem to have inductive biases. And our language model is like that. It can learn impossible stuff. No human being is going to learn. Now, you can, to some extent, in the human case, in a language, you could deliberately, slowly kind of learn something about it, but it'd be like a problem-solving exercise. I don't think there's any reason to imagine it's the kind of language that would ever be learnable. In some cases, they're just clearly not learnable. We had cases where the dependencies are beyond short-term memory capacity. So these models, a human couldn't do it because they couldn't. You repeat a word, 27 times, like that. On the 28th trial, something happens. It's like, well, you can't do that because it's beyond our human capacity. But the models are exploiting that superhuman capacity to perform as well as they do.
When you're science-minded or have a science background like me, and you're talking about all these different, the poverty of the stimulus, and not subjecting how children aren't subjected to words. I mean, I just automatically think about experimenting on my son, and if we just stopped speaking to him all, completely, or started reversing nouns and verbs and
speak backwards. Yeah.
Speak backwards. Yeah. Oh, that'd be rough.
If you could, I think, yeah, exactly. That's the point. It'd be very hard to do that. But give it a go.
Have you? Do you know the phenomenon when? I'm sure you've seen this when, you can take every word in a sentence and sort of flip a couple letters and you still read the sentence fluently, right? And you don't even notice like differences often. And even when they're kind of harsh differences, even if you notice the difference, you can still read the sentence fluently. Maybe this is just another experiment for you to perform to test psychologically these models, how they perform with that kind of with the anagram. I'm not sure what they're called, but every word is kind of an anagram, right?
Mm-hmm. Yeah, we've done actually a little bit like some work like that actually, but and they did surprisingly well actually.
Is that because there's so many typos on the internet, or is there?
It's a good question. In our case, no, I don't think we trained it on typos. So the model. So these letter transpositions. I mean, it's not quite true that if you read a word, you transpose things, you don't notice it. I mean, some words are different, like form and from. I mean, you can read those words. So clearly, many words. And it turns out there are some language like Hebrew. There's some interesting studies in Hebrew where lots of words. I think it's not only Hebrew, but some studies been done in Hebrew where in Hebrew, when you swap two letters, you produce another word. In English, you swap two letters, you end up with just a nonsense thing. But in Hebrew, for just the nature of how it is, and so they're very saliently different. So if you transpose letters in Hebrew, the visual systems learn to be very attuned to the orders of letters. Where in English, because it doesn't matter as much, people are a little bit less sensitive to those transpositions. So so the training environment will impact the extent to which you're sensitive to transpositions. And we found a study. We have a paper that's, I think, coming out now, but it was showing, to my surprise, the model did a surprisingly good job at accounting for the similarity between letter transposition, a word that you transpose something and then you compare it to a word without the transposition, and you ask how similar are those internal representations. And they're more similar than I would have thought. And the pattern of results kind of capture the experimental conditions that people have done. So sometimes these models do, I still think I could make the model fail if I tried harder, but I was, I suppose pleased. I don't know. I quite enjoy finding faults in these models, but credit to a credit too. The model did a good job.
I was going to say, to your surprise, you mean to your chagrin, because you hate these models, right?
I don't.
I know. I don't want to give people that impression, actually.
Psychology just gets no respect. I mean, we need more, people need to pay attention because psychology has beautiful data and relevant data for so many things that somehow people think it's more impressive to look at neuroscience than the relevant behavioral data. So, I mean, the very simple version of this is that, people would kind of, I don't know, do an fMRI scan. You do some instruction on an intervention to try to improve someone's reading skills. And you kind of say, this is the state of it. Johnny has trouble reading. Here's the state of his brain as measured by fMRI before intervention. And then you do some intervention. And then you look, and then you see the brain has changed. The bold signal's different post-test. And you think, oh, the intervention worked. Just like, well, no, we don't know. The question is, does Johnny read better? Behaviorally, that's what matters. And if the reading did change, we know that the brain changed. Where the brain changed is interesting if you're a neuroscientist, but it's just not that relevant to, is it Johnny? I can't remember who I'm talking about.
Johnny.
Johnny. So it's irrelevant to Johnny. It's irrelevant to Johnny's mother. The point is Johnny can now read. And it's the behavioral, you need a careful behavioral measure of the performance of Johnny when reading. We need a good behavioral intervention to kind of, hopefully design a study that has some, logic given what we know about learning and memory. And, so you kind of use psychological insights to design the intervention. You use psychological methods to evaluate the outcome of the intervention to find out whether performance is better. And neuroscience doesn't have any role in any of those stages, I don't think. Neuroscience is just not a useful tool for the teacher or, but it's certainly interesting intellectually. I like to know where Johnny's brain changed after instruction. That's complete. I'm not criticizing neuroscience. I'm criticizing the idea that it's useful for education, and we should invest. And it says, grant funding is a zero-sum game, and the neuroscience studies are expensive. Actually, so are psychological studies where you do, randomized control studies are also super expensive. They're both expensive. Better spend your money if you're interested in education on psychology, not neuroscience. That would be my. That's the sort of the short, but again, the theme is pay more attention to psychology.
I was thinking about naming this episode "Deep Problems with Deep Learning," based on the title of your archive paper, "Deep Problems with Neural Network Models of Human Vision." But now I think maybe I should name it "Psychology Gets No Respect." What do you think? What's a good name for the episode?
I like that. I like that one. Why not? Go for that.
Okay, I'll go for that. But it's going to be attributed to you. Jeff, thank you so much for spending the time with me. We could talk for a lot longer, but it's late in your world and I have to go as well. So I really appreciate it. I had fun.
Yeah, I did too. I really enjoyed the conversation a lot.
I alone produce Brain Inspired. If you value this podcast, consider supporting it through Patreon to access full versions of all the episodes and to join our Discord community. Or if you want to learn more about the intersection of neuroscience and AI, consider signing up for my online course, Neuro-AI, The Quest to Explain Intelligence. Go to braininspired.co to learn more. To get in touch with me, email paul@braininspired.co. You're hearing music by The New Year. Find them at thenewyear.net. Thank you for your support. See you next time.